Today, we're tackling, well, arguably the most fundamental dimension in all of engineering time. We tend to think of it as just, that thing we check on our smartwatches. But the sources we've gathered today make a really compelling case that time is the critical axis, the one upon which all design, analysis, and optimization really have to rest.
That's absolutely right. Yeah. Our mission today, it's really to move beyond just like measuring a ticking clock. We want to dig into how time defines motion, processes, efficiency across every scale imaginable. From how a chemical reaction happens at the atomic level, all the way up to optimizing, say, traffic flow for millions of vehicles in a city.
Right. And the core insight, I think, is that we live in this inherently dynamic world. Everything's constantly moving, changing, reacting. The cooling rate of a turbine blade, the rotation of the planet itself. And time is just the indispensable parameter we use to describe how fast all that motion and change is happening. So let's start with something maybe a bit surprising, a kind of philosophical angle from the sources that grounds this whole technical concept in your own life. It's viewing time as a budget.
Yeah, it's a bit jarring when you first see it, but it's really effective for illustrating scarcity. The source is actually calculated out. If we assume an average lifespan, say 75 years, you're looking at about 657,450 total hours.
Wow. Total hours. And then you have to subtract sleep, right? About a third of that?
Exactly. So take out roughly a third for sleeping, and you're left with a finite resource of 438,300 waking hours.
Okay, waking hours.
And for a lot of our listeners, maybe those just starting college or early in their careers, let's say around age 18,
Yeah.
you've got roughly 333,108 waking hours left. Again, assuming you hit that average lifespan.
333,108. I mean, if that exact number were dollars in your bank account,
Right.
you'd be obsessive about how you spent every single penny. It just immediately puts this real quantifiable value on this dimension we often just let slip by.
And that finite value, that scarcity, it translates directly into this really central engineering idea,
Right.
the difference between steady and unsteady processes.
Okay. We mentioned earlier that time defines change. So a steady process is when the physical property you're looking at, maybe temperature, pressure, velocity, it just doesn't change over time. My favorite simple example is just the length of a metal component, like the casing on your laptop. Assuming the temperature and load are constant, its length is steady, predictable.
Yeah, and that difference between steady and unsteady, it's not just academic, it's crucial. It can be the difference between, say, a predictable utility bill and a catastrophic mechanical failure. An unsteady or transient process is where that physical quantity does change over time. Think about cookies fresh out of the oven cooling down to room temperature. That's unsteady. Or on a huge scale, the thermal cycling inside a rocket engine during takeoff. That's a massive transient event.
That transient response is so critical. Like if you hit a massive pothole in your car, the entire design of the suspension system is defined by how quickly it absorbs and dissipates that sudden transient shock force, how fast it gets back to a steady state. The time it takes to settle, that's a core safety parameter, isn't it?
Exactly. Time is really the canvas where engineers measure predictability and, well, risk.
Okay, so to measure that transient response accurately, we obviously needed standardization. And getting there required this fascinating historical journey. We had to move away from just looking at the moon and stars.
Yeah, early humans relied on lunar cycles, which is fine for seasons maybe, but terrible for coordinating things that take minutes or hours. So that led to things like shadow clocks, sundials, sand glasses, and those quite complex water clocks.
Right. But the real leap, the sources point out, came with mechanical clocks, those weight-driven ones in the 14th to 16th centuries. But the truly modern era of precision, that arrived with the quartz clock in the 20th century.
Quartz clocks are just brilliant. They leverage material science, specifically something called the piezoelectric property of quartz crystals. Basically, you squeeze quartz, it generates a little electricity, you apply electricity, and the crystal vibrates, it oscillates at an extremely consistent rate.
And it's that consistency, that predictable vibration, that defines the modern international standard for the unit of a second, based on the cesium-133 atom, right?
That's the one, yes. The formal definition is, let me get this right, 9,192,631,770 periods of radiation, corresponding to a specific transition in the atom's ground state. Now, you definitely don't need to memorize that giant number.
Right. So what's the actual takeaway from that incredibly specific number? Why does it matter?
The takeaway is the necessity of that level of precision. That kind of atomic stability is what lets us synchronize things like GPS satellites or coordinate global financial trading platforms down to the microsecond. Without it, Our modern world of instant global communication and navigation just, well, it collapses.
Okay. And that need for synchronization, that naturally led to the need for time zones, didn't it? Back in the late 19th century, driven mainly by the railroads, I gather.
Yeah, primarily the expanding railroad companies. Since the Earth rotates 360 degrees in 24 hours, the math is pretty straightforward. Every 15 degrees of longitude equals about an hour difference.
Okay, that makes sense. And then there's the perennial debate, daylight saving time, or DST.
Ah, yes, DST. Historically, it was brought in during hard times, wartime actually, like WWI and WWII, mostly to conserve fuel. The idea is by setting the clock forward, you extend daylight into the evening hours, meaning people turn on their electric lights later.
And the sources mention a U.S. Department of Transportation study showing this also reduces car accidents, which led to the U.S. change in 2007, formalizing it from the second Sunday in March to the first Sunday in November.
Right. It saves energy, apparently reduces accidents. It sounds like a clear optimization win, doesn't it?
It does, but there's always that counter argument, isn't there? If it's so great, why is there this constant push and pull, this debate about getting rid of it?
That's a really good question. And the counter-argument usually focuses on the transient cost, the disruption to our internal clocks, our circadian rhythms. Critics argue that this massive annual disturbance to our sort of internal steady state costs more in lost productivity and, just plain lost sleep than it saves in energy.
So it's a great reminder that even when you're engineering for efficiency, you have to factor in the human element, the human performance limits.
It's a perfect connection back to that steady versus transient idea. Absolutely.
Okay, let's transition then. Let's talk about repetition. This is so central to dynamic machine design, periods and frequencies.
Yeah, the basics are pretty familiar. The period, usually symbol dollars, just the time it takes for something to repeat itself. Like Earth's orbit is about 365.24 days. And frequency, often fun in A, is just the inverse of that, how often the event occurs, usually measured in hertz, which is cycles per second.
Simple enough, but where does this become really valuable for engineers? I'm thinking oscillatory systems, like if you're designing a bridge or a building or a turbine blade, you have to manage its natural frequency, right?
Oh, absolutely critical. Take a simple spring mass system. Engineers might not need the exact formula memorized, but they must understand the relationship. The frequency of oscillation depends on the stiffness of the spring, let's call it turbine, and the mass. Increase the mass, the system oscillates slower. Increase the stiffness, it oscillates faster. It's intuitive when you think about it.
And that lets them tune systems, right? If a machine vibrates too much at, say, 10 hertz, they can change the mass or the stiffness to push that natural frequency somewhere else, maybe 15 hertz, to avoid resonance and potential failure.
Exactly. And here's a cool historical application from the sources. Early oil companies actually used this principle. They used highly sensitive oscillating pendulums and measured tiny changes in their period, how fast they swung, to detect minute variations in local gravity. Why? Because those gravity variations often indicated a denser mass underground, potentially an oil reservoir.
That's clever. And just think about the sheer range of frequencies in engineering. Mechanical systems might deal with low frequencies, maybe 1 hertz up to a few thousand hertz. Then you jump to electronics. Your standard AC wall current is 60 hertz in North America. But a personal computer clock, that can hit 3 gigahertz. That's 3 billion cycles per second. The scale is just immense.
It really is.
Okay, now let's get to the real heart of motion analysis, combining time and length to derive velocity and acceleration.
Right. We can probably assume most listeners know the basic difference between speed, the scalar, just magnitude, and velocity, the vector, which includes direction. But the application is where it gets interesting. You need average speed to estimate your arrival time on a road trip, sure, but you need instantaneous velocity, including the direction, for, say, an autonomous vehicle to safely execute a lane change or avoid a collision.
Makes sense. And acceleration is the rate of change of that velocity over time. And this is the part that sometimes trips people up. Acceleration can happen even at a constant speed.
That's the key insight, because acceleration measures the change in the vector. So if you're driving a car at a steady 60 miles per hour, but you're going around a constant curve, you are accelerating. Why? Because your direction is continuously changing, and that requires a constant force pulling you towards the center of the curve. You feel that force pushing you outward in your seat.
We see this most dramatically, of course, with gravity, the attractive force between masses. Here on Earth's surface, the acceleration due to gravity, the 81 meters per second, square it all. So if you drop something, its velocity doesn't just increase steadily, it compounds, right?
Exactly. After 1 second, it's falling at 9.81 meters per second. But after 2 seconds, it's falling at twice that, 19.62 meters per second. Ignore air resistance for a moment, and the distance it covers increases even faster geometrically over time.
That compounding effect. Yeah, gravity is like the ultimate transient process we always have to account for in design.
Definitely.
Okay, let's shift gears a bit. Let's look at flow, specifically in civil engineering traffic flow. The sources highlight three key variables engineers use: flow, density, Hendrich speed, and average speed. And the defining relationship is simply flow equals density times average speed.
Yeah, and this simple equation perfectly explains the often chaotic nature of rush hour traffic. Think about it. Traffic slow is zero when you're completely stopped, bumper to bumper. Why? Because speed is zero, even though density is at its absolute maximum. Then, as things start moving and speed increases, flow rises, and it eventually reaches some maximum efficiency point.
But here's the critical kind of counterintuitive insight that traffic engineers are obsessed with. Once the traffic becomes uncongested and speeds continue to climb, like when you're really speeding on an open highway, the flow, the number of vehicles passing per hour, actually starts to decrease again.
Right. Why does that happen? It seems odd. It drops because at those really high speeds, drivers naturally and need to leave much bigger gaps between cars for safety. That increased spacing dramatically reduces the vehicle density.
Wow.
So even though your average speed is very high, the total number of cars passing a point per hour actually falls below that peak efficiency point. So engineers are always trying to manage things to keep traffic right near that sweet spot, that maximum flow rate.
That concept of flow, it's pretty much identical when we talk about moving fluids, right? We call it volumetric flow rate, just the volume of a substance passing a point per unit time.
Yeah.
Super important for things like measuring natural gas consumption in your home or sizing the ventilation systems, the HVAC in large buildings.
Exactly. Volumetric flow rate, let's call it QDOS, is simply the product of the average fluid velocity,
Yeah.
alvar, and cross-sectional area, a dollar of the pipe or duct it's flowing through. QDOS to blow hay.
Okay. And this leads to that great aha moment example from the sources about pipeline design. If you need to maintain a constant flow rate, maybe for some industrial process, but you reduce the diameter of the pipe by half, the fluid speed has to increase by a factor of 4 to compensate for that smaller area.
Yeah, the math is simple. Area goes down by 4, since area depends on radius squared, so velocity has to go up by 4. But think about the physical implications. You've just quadrupled the speed of the fluid. That dramatically increases the forces on the pipe walls, the pressure drop. It might mean you need a completely different, stronger pipe material or thicker walls. Time, dictating the necessary flow rate, leads to speed, which dictates the required structure.
Fascinating connection. Okay, finally, let's touch on angular or rotational motion. We're talking about anything that spins. Shafts, gears, hard drives, fan blades, helicopter rotors.
Right, and we measure this using angular speed, usually the Greek letter omega, omegadon. The standard unit is radians per second, but engineers often use the more relatable revolutions per minute, or RPM.
And the engineered world is just full of these rotational extremes. You might have a massive, slow-turning turbine in a power plant, but then a modern computer hard drive spins at, what, 7,200 RPM? And that dentist drill you mentioned earlier?
Yeah.
That can scream along at up to 400,000 RPM. Terrifyingly fast.
It is, and we need to connect that angular motion back to linear motion. The linear velocity, dollars, of any point on a rotating object is simply its distance from the center, the radius dollars, multiplied by its angular speed, omega.
Yeah.
So, dollars omega.
Okay, Voller increase Romega. That relationship seems fundamental, especially for things like balancing rotating machinery.
Absolutely critical. Think about a huge wind turbine blade, maybe 50 meters long. Even a tiny imbalance, a small sick mass way out near the tip, large dollars, combined with the operational angular speed, a omega, translates into a massive linear velocity change for that unbalanced mass. That creates huge oscillating forces, which means significant angular acceleration back at the hub, potentially leading to fatigue and catastrophic failure. So engineers have to control not just the speed, but the rate of change of angular speed, the angular acceleration, to ensure everything stays intact.
Right, like the example in the sources. If an electric motor shaft needs to spin up from 0 to 1,600 RPM in, say, 5 seconds, you can calculate the required angular acceleration. It comes out to about $33.05 text radians per second squared out. And that precise figure becomes a core performance spec for the motor. It defines its power, its responsiveness, its reliability.
Exactly. It all comes back to time and the rate of change over time.
Wow. We really have swept across the engineering spectrum today, haven't we? I mean, we started with the finite time budget of our own lives, which
Mhm.
was quite sobering. Then we used the cesium atom to enforce global precision down to the nanosecond. We leveraged time to manage the flow of traffic and fluids, and we figured out the exact acceleration needed for a high-speed drill bit. It really feels like time is the bedrock, the foundation for every single decision in engineering design and optimization.
It really is. Yeah. And I think the essential lesson, the skill for engineers, is mastering that difference between steady and transient states. Designing systems to maximize efficient, steady flow whenever possible and minimizing the duration and impact of those unavoidable transient events.
So, thinking back to that original idea, that finite time budget for your own waking life, those, what was it 333,108 remaining hours for an 18-year-old?
Yeah, roughly that.
Okay. Well, knowing that life itself is fundamentally a transient process, it has a start and an end, and knowing that engineers are laser focused on maximizing efficient flow and minimizing unproductive friction. How does applying that kind of engineer's mindset maybe change how you view your own remaining time?
That's the provocative thought, isn't it? What steps could you take or do you take to make your own life process maybe a bit more steady in pursuing meaningful goals? How do you maximize the flow of meaningful activity and minimize the time wasted on personal or professional friction on things that just drain that finite budget? That's maybe the most important calculation worth running.